So let's look at variable loads and let's try and make it unsymmetric. So we'll have a point load on one end of the bench. Could be caused by someone sitting there, or go on a pogo stick on top of the bench, anything at all. And now we're going to have to work out the bending moment diagram again, before. The same thing is going to be true as when we looked at the self-weight of the beam. And that's that as we move away, the bending moment is going to increase from 0 on this side. But instead of being a squared relationship, what we're going to have is the magnitude of the point load, so capital W, multiplied by the distance from the place where the load is acting at the end. Again, we can call it X, it's Wx. So our bending moment diagram, on this side at least, is going to be relatively simple. We're just going to get it linearly increasing up to a maximum here at the support. What's going to happen here? Well, if we imagine a case where there was no left-hand side of this bench, it wouldn't make any material difference as to how this load was supported. So it's not going to show any behavior, it's not going to be stressed at all, there's going to be no bending. For this case, we can effectively ignore what's going on the left-hand side. But this load is going to have to get down to the ground somehow. It's going to have to get to the ground through the column, and there's this moment, it's going to have to be transferred to the column via bending. Now there's no force acting over this distance here, so we'll have a moment here at the top of the column. There's also no horizontal reactions expected here at the bottom. This horizontal reaction is going to be 0, because for horizontal force equilibrium there can be nothing else acting. So this moment isn't going to change, but you can just plot it as a straight line. It's basically going to be a constant moment in the column caused by this load on the right hand side. So now we come to the shear force, and hopefully by now you know a few tricks. And because we know that the shear force is the derivative of bending moment, we can use what we've plotted on the bending moment diagram to basically guess what the shear force is going to be. And we had a linear bending moment here, so linear term, differentiate it once, we get just a constant term. So we're going to have a constant shear force here. Here we had no bending moment, we're going to have no shear force again. And on this section here, we had a constant bending moment. First derivative of constant term, again, is 0. So this is our shear force diagram. Very easy, just a constant shear through here and nothing else at all in the diagram. And when we come to looking at deflected shape, again, we want to start at the support where we know what's going on. Now, we saw some bending in this column, so there's going to be a bit of curvature. There's going to be no curvature at all at the support. So we start off just going vertically up. But then you can just kind of think about it qualitatively. If this load is pulling downwards, what's it going to make the column want to do? It's going to pull the column over to the right-hand side. So this column is going to start to bend a little bit to the right-hand side. There we are. It's going to bend like this. We're going to have a right angle at the top, because again, we don't expect any bending in the connection. So this right angle is going to start at the top, and then it's going to kind of go downwards like this towards the end where we've got the load. And this section here, there was no bending, there's going to be no curvature. We expect there to still be a right angle at the connection. So this beam is just going to come out like that. It's not the best drawn deflected shape diagram in the world, but hopefully it demonstrates the key points.